In this video, we're going to look at a piecewise Fourier series example. So I want to start right away with the example. So I want to find the Fourier series for this function f of x, which is this piecewise function that equals x squared if we're on the interval where x is in between negative pi and 0, and it equals 1 if x is in between 0 and pi. So I want to begin this problem by drawing the graph of this function. So our function here, f of x, so let's draw our xy axes. All right, so I'm going to draw the x squared piece first. So this exists between where 0 is on the x-axis and between where negative pi is. So let's say this is where negative pi is. Okay, and because there's no equal signs on these inequalities, that means we're going to have an open circle at both of those endpoints. So if we were to plug 0 into x squared, we get 0 out. So that corresponds to this point right here. When x is 0, the output, this is giving me a 0. And when we plug in negative pi into this, we'd get pi squared as the output. Okay, so I start off my graph here at sort of 0, 0 with an open circle. And then it has the same shape that x squared would have until I reach negative pi, and then there's an open circle there. So open circle at negative pi, comma, pi squared. And now let's draw the function 1. Okay, so when x is 0, there's going to be an open circle corresponding to this y value at 1. And then the function stays horizontal like that at 1 until I reach x equals pi. And at x equals pi, there's an open circle because x is not allowed to be equal to pi in this formula. So the endpoints of this interval, the pi and the negative pi, they are the negative L and the positive L here. So in this problem, L equals pi. So let's find the Fourier series. So we want to approximate f of x in this form. All right, so what we need to do now is we need to figure out what these coefficients are. So let's start off with a constant coefficient. So let's figure out what a naught over 2 is. So a naught over 2, remember, using our formula for this, it's the inner product of the function f of x with 1. So 1 is sort of like, it was our constant term in the orthogonal basis that we're sort of trying to project f onto, and then divided by the inner product of 1 with itself. Right, so we saw this formula in the last video. All right, so now each of these inner products is an integral. So the integral on the top goes from negative pi to positive pi, f of x times 1, which is f of x, dx. And then on the denominator, we'll have the integral from negative pi to pi of 1 times 1, which is 1. All right, so we have this fraction. So on the numerator, I need to integrate the function f of x from negative pi to positive pi. But the function is piecewise, so I need to split up my integral into 2 pieces. So the first piece will go from negative pi to 0, because that's where the function sort of transitions from one formula to a different formula. Okay, and on that interval, f of x is x squared. And then the next interval would be from 0 to pi, and on that interval, f of x is 1. So I'm going to be integrating 1. And then if I take the integral of 1 from negative pi to positive pi, that's pretty quick to check that we end up getting 2 pi. All right, so now let's knock out these 2 derivatives on the top. All right, so let's do the antiderivative of x squared. So that is going to be x cubed over 3, evaluated at 0 and negative pi. And then the integral of 1 from 0 to pi, that ends up being just pi. And the denominator is 2 pi. So if we plug 0 into this, and then negative pi into this, and then subtract, we'll end up getting pi cubed over 3. And then we still have that plus pi. And then divided by 2 pi. And now we can simplify this. So we could cancel a pi from the top and the bottom to give ourselves pi squared over 3 plus 1 over 2. And then if we get a common denominator, this will simplify to pi squared plus 3 over 6. So that is what a naught over 2 is. A naught over 2 ends up being this. That was our constant term. So next we want to find an when n is greater than 0. So these are going to be the coefficients of all those cosine terms. So remember, our formula for this is, now we take the inner product of f of x with the cosine terms. So normally we'd write n pi x over L here. But in our problem, remember what L is. L is pi. And because L is pi, the pi on the top and the bottom would cancel. And this would just end up being cosine of nx. So I'm going to write the simplified form of it for our problem. All right, and then on the denominator, we'd have the inner product of cosine of nx with itself. So if we think about Fourier series in terms of orthogonal projections, what this coefficient here represents is, it's sort of the coefficient we get when we project f of x, our function, onto this cosine of nx term. All right, so now let's evaluate these inner products. And whoops, I put a parentheses here. That should have been an angled bracket for inner product. So the inner product on the top is the integral from negative pi to positive pi f of x times the cosine function, cosine of nx dx. And then on the denominator, we have the integral from negative pi to positive pi, cosine times cosine, that's going to be cosine squared nx dx. So we saw in the last video that when we take the integral of cosine squared from negative L to positive L, that will end up being L. So in this case, my L is pi. So the same thing was true about sine. When we integrate sine squared of the n pi x over L from negative L to positive L, that also ends up just being equal to L. So we saw that in the last video. All right, so now let's continue to simplify. So our integral in the numerator, we have to split up into two pieces. So from negative pi to 0, f of x becomes x squared, and then times we have cosine nx dx. And then we'll have another integral from 0 to pi. And on that interval from 0 to pi, f of x is 1. So we'd get 1 times cosine nx, which is just cosine nx. All right, so that is what we have in the numerator. So the denominator now we know is pi. So at this point, we need to determine what these two integrals are. So one is just cosine of nx, one is x squared times cosine of nx. So I'm going to start off with cosine of nx because that's easier. So let's do this integral first. So for this one, we don't need any special techniques like u sub or integration by parts or anything like that. We can just actually eyeball this integral. So the antiderivative of cosine of nx is equal to sine of nx divided by n. And then we have to evaluate this at pi and 0, and then subtract. Okay. So if you didn't quite see how I got that antiderivative, we could do this with a u sub. You could let u be equal to nx. And if you did that, you should get the same answer. All right, so now let's go ahead and plug in pi and 0 into this. So if we do that, we get sine of n pi divided by n, and then minus plugging in 0, we'll get sine of 0 over n. So clearly sine of 0 is 0, so that means this fraction is going to be 0. So sine of n pi, so maybe you might know what this is. So remember here, n is an integer. So n is an integer. So you might know what this is, what sine of n pi is. But I want to do a brief aside just to do a quick review, because when we do these Fourier coefficients, when we calculate them, we end up seeing sine of n pi and cosine of n pi a lot. So I want to do a brief review for what those are. So if n is an integer, let's look at each of those. So if we have sine of n times pi, so n is an integer, so this will be something like sine of pi, or sine of 2 pi, or sine of 3 pi. Or I could do negative integers, like sine of negative 5 pi. All of those are going to be 0. So really make sure you see why. Why is sine of an integer times pi equal to 0? All right. What about cosine of n pi? So this is stuff like cosine of pi, cosine of 2 pi, cosine of 3 pi, even negative integer multiples of pi. For this one, there's two cases. So if n is odd, that'll give us one answer. And if n is even, that'll give us another answer. So if n is even, we're going to get values like cosine of 2 pi, or cosine of 4 pi, or cosine of 6 pi. And those are all 1. If n is odd, we get stuff like cosine of pi, or cosine of 3 pi, cosine of 5 pi. And those will all be negative 1. So cosine of n pi sort of alternates back and forth between being negative 1 and being positive 1. Okay, so cosine of n pi. So how do we express this function that's sort of switching between negative 1 and positive 1? Well, we write negative 1 to the n. So this is something that you likely may have seen back when you talked about a series in calculus. You would have seen stuff like negative 1 to the n show up a lot when you have an alternating sequence or an alternating series. All right, so using that for our problem, now we know that sine of n pi is going to be 0. So that's kind of nice. This whole integral right here ended up being just 0. But what about that other integral that has the x squared? So how do we do this integral? So this one's not as easy, but it's not too bad. It is a little bit tedious, it turns out, to do it. But since this is kind of the heart of the problem now, determining what this is, pause the video for about 3 minutes and try to evaluate what this integral is. The integral of x squared cosine of nx. 4, 3, 2, 1, pause the video. Pause it for about 3 minutes and try to evaluate this integral. So really make sure that you're seizing this time to actually pause the video and try this, because we encounter integrals like this all the time with Fourier series. All right, so hopefully you've paused the video to try this. All right, so I'm going to continue this integral below where I have some more room. So to integrate something like x squared times this cosine function, we need integration by parts. Integration by parts. Or sometimes I'll abbreviate this as IBP for integration by parts. So if we do integration by parts, we need to say what u is and what du is, and then what dv is and what v is. Okay, so we start off integration by parts by figuring out, well, what is u and what is dv? So u for this problem, I want to let it be x squared. And the dv, I'm going to let it be the other stuff. I'll let it be cosine of nx dx. So sort of the conceptual reason why is, whatever I let u be in integration by parts, I'm going to end up taking the derivative of that to form du. So if the derivative of this term that I let be u is simpler than what u was, that means it's probably a good choice for u. So what I mean by that is, if we take the derivative of x squared, we get 2x dx. And that's a simpler looking thing than x squared because it has lower power. All right, and then if we take the antiderivative of cosine of nx to get v, we'll get sine of nx over n. All right, so we have the setup for integration by parts. Now let's go ahead and use our integration by parts formula. So if we do that, our integration by parts formula, so remember it'll be uv, but we're evaluating at points now at negative pi and 0, and then minus the integral from negative pi to 0 of v du. So that's our integration by parts formula. And now let's go ahead and plug into this. All right, so uv will give us x squared sine nx over n. So that's the uv. And then evaluate that at negative pi and 0. And then we have minus the integral from negative pi to 0 of v du. So when we multiply the v and the du together, some of these terms are constants. So this 2 is a constant. I can move that to the front. And this n on the denominator of sine of nx, that's a constant. I can move that to the front. And then inside the integral, we will still have x and sine of nx. All right, so we did integration by parts. We have this uv term at the front, and then we have minus the integral of v du. And notice that this integral is now a little bit easier than the one I had before. Because before, we had to figure out, well, what was the integral of x squared times this trig function? So we had this polynomial of degree 2. Now, at least we've reduced the degree of the polynomial we have, because now we have x to the 1 power. But still, we are going to need to determine what this is, what this integral is. So at this point, pause the video one more time if you didn't get this far before, this time for about 1 to 2 minutes, and see if you can determine how do we evaluate this integral. And once you know, go ahead and start to do it. 4, 3, 2, 1, pause it. Pause the video one more time and try this for a minute or two. All right, so how do we do this? How do we evaluate this other integral? So we actually need to use integration by parts again. So IBP, integration by parts again on this. All right, so when we do integration by parts, I need to say what u is and what dv is. And then from there, I'll get du and v. So I'm going to let u be the polynomial term, the x, because its derivative will be simpler than it. Du, its derivative would be dx. Technically, it's 1 dx. dv, I'm going to let be the other stuff, which is sine of nx dx. So then the antiderivative of that would be negative cosine of nx over n. So that's my integration by parts setup. So now let's go ahead and evaluate this integral. So I need to figure out what the integral from negative pi to 0 of x sine nx dx is. So using integration by parts, I'll get, sorry, let's write this x better, x times sine nx. So I'll get uv first. So that'll be minus x cosine of nx divided by n, and evaluate this at negative pi and 0. And then we're going to get minus the integral from negative pi to 0 of v du. So v du, so for that we're going to have negative cosine nx over n dx. But notice that we have a double negative, this negative and this negative, so those will become a positive. All right, so we have this. So let's go ahead and start to evaluate these. So if we plug 0 into this first term here, we'll get 0 times some cosine thing, but 0 times anything is 0. So plugging in 0, we get 0. And then we're going to have minus what we get when we plug in negative pi. So if we plug negative pi into this, well, we have this negative here. Okay, and then you plug in negative pi in for the x, and then times cosine of negative n pi, and then that whole thing divided by n. Okay, and now we need to take the antiderivative of cosine nx divided by n. So that antiderivative will be sine of nx. We'll get a sine of nx for the antiderivative of cosine, and then another n will sort of need to come to the denominator. So the denominator will now be n times n, which is n squared. And we evaluate this at negative pi and at 0. Okay, so let's simplify this. So notice I have a negative, negative, negative. Overall, that just gives me one negative. So we have a negative pi, and then cosine of negative n pi is also negative 1 to the n. because cosine of negative n pi is the same thing as cosine of n pi, because cosine is an even function. All right, so we have this, and then over the denominator, so the denominator was n, and then if you plug in 0 into sine of nx, you get sine of 0, which is 0. If you plug negative pi into this, you get sine of n times negative pi, and that's also 0. So this whole thing will be 0 after you plug in the 0 and the negative pi. All right, so we have now figured out what this integral is, the integral of x times sine of nx. We need to now multiply that by negative 2 over n. So let's do that next. So multiplying this by negative 2 over n, so we are going to get negative 2 over n times the formula that we just got for the integral, which was negative pi times negative 1 to the n over n. So multiplying this out, the negative times the negative becomes a positive. So we get 2 pi negative 1 to the n over n squared. All right, so now why did we need to do this? So we've done a lot of computation, a lot of antiderivatives. Remember earlier, we were trying to figure out what these two integrals were. So we've now figured out what the integral of the x squared cosine nx term is. It's just what we finished deriving. So let's go ahead and plug that back into this whole fraction. All right, so let's scroll it down and plug those things in. So let's scroll it some more, scroll it some more. All right, so what we end up getting is an equals this fraction right here. So notice I've plugged in this 2 pi negative 1 to the n over n squared for that x squared cosine integral. The other integral that we had above was 0. And that whole thing was divided by pi. That's what we had on the bottom. So if we cancel a pi, we end up with this. 2 times negative 1 to the n divided by n squared. So that is what a sub n equals. That's what a sub n equals. And this is when n is greater than 0. All right, so what's left for us to get is the coefficients of the sine terms. So for the coefficients of the sine terms, we call those b sub n. And these are, so remember, formula for this is it's the inner product of f of x with the sine term. And again, the reason why it's just nx is because I've already gone ahead and plugged in what L is. L is pi here. So that's why we don't see n pi x over L. It's because I've plugged pi in already. And then divided by the inner product of sine of nx with itself. All right, so we know that both of these are going to be integrals. And the integral on the top, we're going to have to split up into two pieces. So one piece from negative pi to 0 of f of x times sine nx. So sine nx. And what's f of x on this interval? It was x squared on this interval. And then we also have an integral from 0 to pi, and f of x on that interval was 1. So I won't write that. And then 1 times sine nx is sine nx. So that's what we get on the top. So remember, I mentioned before that this thing on the denominator is going to be equal to L. So that's the case for the coefficient of the cosine terms and the coefficients of the sine terms. It's not necessarily true for the constant term, for the a naught over 2. For the constant term, it turns out that this will end up being 2L. So the denominator for the constant term will end up being 2L, which in this case was 2 pi. All right, so in our case here, L is pi, so my denominator is going to be pi. All right, so for these integrals, I'm not going to go through the entire computation because it ends up being pretty similar to what we did above. I'm just going to mostly just say what we end up getting. But I'd encourage you to check this because being comfortable with these types of derivations is really key to handling these types of problems. All right, so when we end up doing this second integral, it will end up being 1 minus negative 1 to the n over n. After we do the antiderivative and sort of plug in, this is what we get. With this first antiderivative, x squared times sine nx, it's really similar to the x squared cosine nx we had above, where we needed to integrate by parts twice. So for this one, we'll integrate by parts twice. So I'm just going to go ahead and say what we end up getting. So after we do integration by parts twice on the sine term, we end up getting this fraction here at the front. So it's a little bit more complicated looking than the fraction we got for the cosine coefficients, but this is what it is nonetheless. So now that we have that, we are ready to write down our Fourier series. So after we plug in for our coefficients, so maybe let me highlight this one in green. So these are the coefficients of the sine terms. And I've gone ahead and gotten a common denominator and simplified this a little bit more. So the coefficients of the sine terms are here. The coefficients of the cosine terms, that's what we got. Ooh, that's the derivation that we just did before this. Let's do a different color. So that one we worked out together fully, and the constant term was this. All right, so that is our Fourier series. What I want to end this video by doing is using Desmos to graph these, to graph this Fourier series, and just answer the question like, is it close to my function here? And actually my function wasn't x. I forgot to write f of x. Right, so our function wasn't x here, it was f of x. So our function f of x, our piecewise function, is approximated by this Fourier series. So let's do a Desmos demo to see like how good is this approximation. All right, so here we are in Desmos, and I've gone ahead and plotted our piecewise function. So we got our x squared piece, and then we have this y equals 1 piece. Okay, and then you might see that in my formulas section here, I have a bunch of complicated looking sigma formulas. Okay, and that's because I've sort of entered in our Fourier series and certain terms of it. Okay, so what I want to do first is I want to look at what the Fourier series would be if instead of having an infinite sum, if we just had, if a up here was 1. So if we select that graph, we get this sort of, sinusoidal graph here, and it's not really a great approximation of our piecewise function, but that's what it is nonetheless. So what if I took two terms? If I took two terms and I look at that graph, I get this blue graph, and it looks a little bit better than the red graph, like at least it's following this parabola a little bit better, but still not great. What about if I took 3 terms? If I take 3 terms, I get this green graph, and it still doesn't look great, but it's getting a little bit closer to the parabola. So now let's get rid of some of these initial graphs that I've drawn. I'll get rid of the first 2 so I can see this last one a little bit better. So notice, yeah, it's pretty close to the parabola, at least for part of it, and then the line, it's not super great. So what I want to do next is I want to show you an animation of what the Fourier series looks like if I let a get bigger and bigger and bigger, if I take more and more terms. All right, so here is what our initial graph looked like. So I'm going to click this play button, and as the play button goes, what's going to happen is the a is going to get larger and larger and larger. And let's look at what happens to the graph. So a is getting bigger and bigger and bigger, and notice that our graph is now hugging this parabola super, super closely. Even the line, sorry, it kind of just repeats. It repeats when I get to 100. But yeah, so the bigger a gets, the closer that our Fourier series gets to our function, the better it is as an approximation. All right, so let's pause that. All right, so now there's one other thing that I want to sort of point out about this. So our Fourier series was, getting really, really close to the parabola and to this line. But what happens at this discontinuity point? What happens at 0, for example? So if I draw in our Fourier series again, it was this, and this is when a is, let's go bigger for a. Let's go like 50. So that's when we're taking 50 terms. Where's the Fourier series going? At 0. I can zoom in a little bit there. I can zoom in, And, you know, it looks like the Fourier series might be going halfway through between where 1 is and where 0 is here. So I've actually gone ahead and entered in that point. Let's plot it. And it looks like it's going through there. Let's zoom in more to see if that seems realistic. Zoom in, zoom in, zoom in. Yeah, it does look like the Fourier series is sort of going through there. It turns out that that is what happens with the Fourier series when my original function has a jump discontinuity. The Fourier series will sort of converge to this like midpoint of where the function sort of was on one side of that discontinuity. So on one side it was up here at 1, and on the other side it was sort of getting really, really close to 0 here. So our Fourier series sort of approached that midpoint. The other thing that I want to sort of mention is, well, what happens to this? Sorry, what happens to this at the end points of our interval? What does the Fourier series sort of converge to at pi and negative pi? All right, so let me unselect this point. So at these endpoints where sort of the parabola begins and where this line segment ends, where's the Fourier series going through there? So I'm going to go ahead and select these points. So these points have now shown up. What these points are they're sort of like the average of where my function was at this right endpoint, and that was the y value was 1, and where the function is at this left endpoint, and that y value was pi squared. And that's what I've entered here, 1 plus pi squared over 2, the average of those y coordinates. And we could check this. We could zoom in a little bit more to see if this is believable. Zoom in, zoom in, zoom in, zoom in. Yeah, my Fourier series does seem to be going through that point. And if we were to check it at that other endpoint on the left, the same thing is going to be true. Another thing that we can sort of observe about this Fourier series is notice that if I were to zoom it out, even though my function only sort of occurred on this interval from negative pi to positive pi, the Fourier series keeps going, you know, forever in the negative direction, and it keeps going forever in the positive direction if I decided to look that way. Alrighty. So in the next video, we're going to talk about this idea of what the Fourier series actually converges to in more rigorous detail.